Alright, let's go ahead and let's look at counting today. So we've spent quite a bit of time developing discrete mathematics from logic to sets, relations. We struggled a little bit with cardinality and countability. And from countability, we talk about infinite sets and countable sets and all that good stuff. We're gonna scale it down and come back to the finite world and work with finite sets. And now we want to develop a few ideas on how to count, and we'll see some of these counting ideas later on when we solve problems pertaining graphs and trees. So let's start off with a relatively straightforward claim that if you have A and B as finite sets, then you can calculate the union through this equation. And perhaps we can illustrate this with a picture. So this is going to be representing A, this will represent B. And the idea is how many items are there in A union B. Based on this, the idea is almost like to split this up, this whole region, into two portions. The A portion, correct? The A portion and the B portion. And once we can split this up, then we can add the constituents in these two regions because they do not overlap. So the idea here is that A union B can be written as the union of two sets that do not overlap, like this. So that allows us to add the items. And along the way, I'm gonna need you guys to help check some of the statements which I claim during the stream, because these statements can be a little bit distracting from the main proof. I'm gonna show the essential idea of the proof, and there'll be some details that I'll leave for you guys to check. You can use your existing proof techniques to go about those as well. And what this tells us, okay, so why we can do that is because A intersect B excluding A is empty. In fact, the first one, you need to check that that the union does indeed check itself out. So I'm gonna include all of these guys here. And you can treat these extra statements as exercises. Right, so maybe I'll denote exercises using a green star. So green star will represent an exercise with which you can help to verify and make sure that our claim is legitimate. Okay, now the next part is the observation that this B excluding A bit over here can really be written as B excluding A intersect B. Right, so roughly speaking, B excluding A refers to this, well, crescent-ish shape, which is all of B excluding away this middle bit, and this middle bit is A intersect B. So once again, you can go ahead to verify that this statement is legit. You can check this out using set properties. This is a really good exercise in using the ideas from sets to derive certain results. And finally, because A intersect B, you're sort of removing that from B, so we can subtract. And the justification here is that A intersect B lies inside B. Now this is pretty obvious, but you can go and try to prove it using some definitions if you wish. And that establishes what we call the inclusion-exclusion principle. And in this situation, we're working with two sets. For two sets. So that means that A union B equals to A plus B minus A intersect B. If we've done a bit of probability theory before, so let me highlight this little neat parallel in the notion of probability theory. In probability, you will get a very similar result. In fact, it's almost, the proof is basically the same. You're using the properties from probability theory. that probability of A union B is probability of A plus probability of B minus probability of A intersect B. And so that's the probability inclusion-exclusion principle in the context of probability. And there are uses for it, but there is a really useful result that's coming up later on that will be useful in any area of data science, computer science, math that you're working with. Anything that requires probability, there's a really useful result which we can explore in just a moment. Now I'm actually going to copy and paste this guy because we are going to need this for this next claim on the inclusion-exclusion principle for 3 sets. And once we have that, then that's the next question. How do we sort of make sense of the 3 set situation? Well, we could try to draw 3 sets and apply the same logic, but now we have to deal with a lot more regions. That's the first troublesome bit. And the second troublesome bit is it's really hard to extend to 4 sets. So what's the strategy over here? Now, there are a bunch of strategies and you could attempt all of them if you wish, but we're going to use a very similar strategy to what we did just now, right? Because if we look at this observation really carefully, well, there are a few ways to think about it. If you want to go ahead directly, you can write this as A union B excluding A union C excluding all of A union B. So more precisely, you could write A union B union C as A union B excluding A union C excluding A union B. Correct? And you could literally apply the same reasonings and slowly work your way through. That being said, the algebra would still get rather clunky. So I am going to propose that we use the 2-set situation to prove the 3-set situation. And we can use this to prove the 4-set situation and so on and so forth. So let's go ahead and prove this claim. And let's write it this way. So A union B union C can be written as A union B or union with C. And the idea is that when we take the cardinality, we can apply the 2-set inclusion-exclusion principle over here to get A union B plus C minus A union B intersect C. And now we can do a little bit of algebra. I will show the algebra here, but for the next few questions, you guys can do the algebra on your own. But the strategy is a bit more crucial. So the first bit of algebra is to apply the rainbow method of the union over the intersections. So that will be A intersect C union B intersect C. And now we have inclusion-exclusion. We have a union of 2 sets and a union of 2 sets again. And this allows us to apply inclusion-exclusion a second time. Now this is the n equals to 3 case, and I want to show you how it works for n equals to 4 case, because that will help you generalize in the most general situation. But in this situation, we can unpack A union B to get A plus B minus A intersect B. C will just remain as C. And then this union of sets can also be expanded using the inclusion-exclusion principle. So let's put a bracket over there. And let's write this as A intersect C plus B intersect C minus the intersection of the sets. This is by the inclusion-exclusion principle for 2 sets. We can clean up a bit on the inside the white underlined stuff, and that will give us this expression. So this will be A intersect C, B intersect C, A intersect B intersect C. Now right here, we want to you might need to do a quick check that A intersect C intersect B intersect C really does give A intersect B intersect C. You might want to do a quick check on that. But once we expand out all of the brackets, we consider all of the algebra, we can collect all of the one set terms, collect all of the two set terms, and collect all of the three set terms. And that is sort of the way we can derive the inclusion-exclusion principle for three sets. Now, very naturally, we might want to ask, can we do this for 4 sets? And the answer is yes, we can do it for 4 sets. So, here's the statement for 4 sets. It's a long statement, and I'm gonna leave some of the details for you guys as an exercise. But here's the strategy. Let's start with the strategy. Once again, A union B union C union D can be written as the triple union, union with the D. We can take cardinality. We can apply the inclusion-exclusion principle for 2 sets because we have these 2 sets which we can apply it to. And then we can expand out this expression using the Rainbow method, distributivity. And now you'll notice that these guys are unions of 3 sets each. And this allows us to apply inclusion-exclusion principle. And I will leave you guys to check that. If you apply the inclusion-exclusion principle, the first term will simplify to this expression. That will be the first term. This first term will simplify to all of this. The D will just remain as a D over there. And this other collection over here is going to simplify in a rather convoluted but nevertheless relatively straightforward manner. And you're gonna get a little bit like this. Whoops. You're gonna get something a little bit like this. So it'll be this. Let me include the negative symbol over here. Actually, let me include the negative symbol in the calculation. So if you expand out using the inclusion-exclusion principle for 3 sets, this is what's gonna result. This will materialize over here. Oops. This should come at the bottom. Okay. And you're going to get these expressions. Okay, when you add them all up, you're going to get the final. You're going to get the final result over here for inclusion-exclusion. And a very natural question to ask is, if you can do it for 2 sets, 3 sets, 4 sets, can you do it for n sets? And the answer is you can apply the same reasoning and prove by induction that for the n set situation, you get this expression. Now, this looks a really complicated expression, but just to illustrate the point, if we were to set n equals to 2, meaning the two-set situation, we're going to get the union from I equals to 1 to 2 of ai. This will be equal to summation I equals to 1 to 2 minus 1 I minus 1 summation j equals to I intersect j in j a j. Just to illustrate the point that this is indeed the general situation for the inclusion-exclusion principle, we can unpack when I equals to 1. So we can consider I equals to 1 here, and then I equals to 2. For I equals to 1, we are going to get minus 1 to the 0 summation summing over all of the sets where it has one element, right? And then where there's one index, and it will be j in j a j plus minus 1 to the 1 summation j equals to 2 intersecting a j. And what we obtain over here, if we were to slowly check, well, for size of j equals to 1, we only have either j equals to 1 or j equals to 2. So that gives us, we'll get intersecting j in the set containing 1, aj, plus j in the set containing 2, aj, minus j in the set containing 1, 2, aj. And let's unpack this definition over here. If we consider j in 1, then there's only one option. That will be a1. If it's j in 2, there's only one option here. That will be a2. And then if j is 1 and 2, then you're getting an intersection of a1 and a2. However, on the left side is the union of two AIs. So we do in fact recover the basic inclusion-exclusion principle for two sets. This is just a check to see that this generalization works out very nicely. It's a pretty long and tedious exercise. If you don't feel like doing it, it's not a big deal. But there is a way to generalize it if you wish. Now that being said, there is, I mentioned earlier on, a really useful result from all of these expressions here. Now, there is one item over here, okay, and here's the little surprising fact. Okay, so I'm going to copy and paste this. And yes, this is the inclusion-exclusion principle for n sets. But as you can see, it's a really unwieldy expression. So there's actually a much more useful expression for us. I'm going to express this in both the number of elements approach as well as the expression you would probably see more often in probability. And this is the claim. The claim is that the union of n sets, and this is way more powerful, is upper bounded by the items in each set. Right, so the idea, for example, the union of a1 and a2 will be upper bounded by a1 and a2. This is what we call the union bound. It's sort of like a triangle inequality, but that's more technical. And this is what we call a union bound. This is called the union bound. Let me write it over here. And it's a really powerful result because it's really unwieldy to work with the exact expression. But if you can work with something way simpler and that is not too far off from the actual answer, the union bound is precisely what you need. Now, of course, there is a trade-off. For such a simple formula, we trade off because we don't get an exact equality in any and every situation. But this upper bound can be really, really useful when dealing with what we call asymptotic proofs, where you need to show that the algorithm performs nicely when given a large amount of input. Now, that's the claim, and here is the probability version. I'll call this the probability version. And that is the probability of the union is bounded above by the sum of the probabilities. This is the probability version, and this is the really much more useful one, because most algorithms, you can only hope to make sure that probabilistically it works out. Right? Most algorithms can be analyzed using probabilities. So that's the element over there. That'll be an interesting idea. So that's sort of the union bound. It's a really, really useful idea. And you'll probably find this idea to be really, really helpful in your studies in computer science or mathematics and whatnot in the future. For those doing math, this is basically what we call the triangle inequality. If you were to phrase things properly, you get a triangle inequality essentially. And if you are in probability theory, or rather if you are in computer science and business analytics and all of the good stuff, applied mathematics, you would definitely find the union bound to be really, really useful. So there's a place for everyone in terms of this particular result. And we'll learn a few more interesting results on counting graphs and trees in the upcoming streams, which will happen in the coming days. And we will now proceed to do a bit of counting, since we are getting used to the idea of counting. So here's the question: fix m and n in the integers. We will let a have size m, b have size n. So perhaps we can draw a quick picture over here. So here's a. Here's size m, and here's b. Here's size n. So the first question is, how many relations are there from A to B? So in other words, here's the question. We are trying to find the number of relations from A to B. Now, to calculate the number of relations from A to B, we might want to first ask, what do we mean by a relation from A to B? Now, if you have forgotten what a relation is, you can go check out the stream or the video on relations. And over there, we define a relation as a subset of A cross B. It's a choice of connections from A to B. This is represented by ordered pairs, and therefore every subset of all of the ordered pairs will give you a relation, and vice versa. So we need to count the number of subsets of A cross B. But the number of subsets of A cross B, well, if we consider all the different subsets of A cross B, that simply gives us the power set of A cross B. And the power set of A cross B contains all the different subsets. So we're trying to find the cardinality of the power set. And surprise, surprise, how do we go about this? Now, some of us are very aware of the result, but for the benefit of those of us who have not seen this result, let's do a quick check. We'll let A, or rather we'll let S be a finite set, and suppose that it has size n, just to keep things simple. The power set of S is the collection of all subsets of S, right? So it's all the A such that A is a subset of S. And what we need to do is to count the number of subsets of S. Now, how do we go about doing it? So here's the question. S can be written as x1, x2, all the way to xn. Now, that it will be S. Now for any subset A, I'm going to ask the question, do I want to include x1 or not? Well, I can include x1, I can exclude x1. If I include x1, that's one possibility. If I exclude x1, that's another possibility. So whether I want to include x1 or not, there are a total of two possibilities. What about x2? Well, again, I can choose to include it or exclude it. So that gives me another two choices on top of my initial two choices. So each of these two choices has two more choices. And now we have four choices. Each of these four choices, we can either include x3 or exclude x3. And this gives us another two choices all the way to the last element. So at every stage, there are a total of n stages. And in each of these stages, you're making two choices. And these stages are happening one after another. This tells us that the total number of choices is 2 for the first stage, times 2 for the second stage, times 2 for the third stage, and so on and so forth. How many stages do we have here? This is going to be 2 to the n. And this is what we mean by 2 to the size of s, because the size of s is n. And sometimes you might see in higher level mathematical, quantitative related areas, sometimes we would even abbreviate the power of s just to remove any ambiguity. We would write this as 2 to the s. And the idea is that when s is finite, the modulus of the power set of s is precisely 2 to the modulus of s. We proved this relation here, but math people and computer science people and all that good stuff, they like to use this notation to compactify what they mean by a power set. Now what that means is that we can come back over here, and the number of elements in the power set of A cross B is precisely 2 to the number of items in A cross B. Now, how do we calculate the number of items in A cross B? Well, every item in A, how many options do we have? Well, A cross B, in fact, we might need to sort of very quickly recap what we mean by A cross B. A cross B is the collection of ordered pairs, where A is in A and B is in B. And we have a total of, if A has m elements, we have a total of m choices for A. We have m choices. And if B has a total of n elements, each of these m choices has n more options. So if each of these options, the first option you have a total of n, the second option you have n, the third option you have n, you essentially have m multiplied by n options. And that means that we can write this as 2 to the mod A mod B, and we can finally plug in mod A to be equal to m and mod B to be equal to n. Now I believe we have names for this. This is called the multiplication principle. There are technical ways to prove these claims, but for problem solving processes, this should suffice. I think that's more than enough, if I'm right. Okay, great. Now, so we are going to ask another question. So we previously asked about the question about the number of relations from A to B. We asked for the number of relations from A to B. Now we're gonna go one step further. Functions are a special type of relation, where every input has exactly one output. So now the question is, how many functions are there from A to B? So we can think about it this way. For each of these inputs, we must find exactly one output for them. For the input x1, how many choices of outputs do we have in B? We have a total of n choices, because it's y1 all the way to yn. So for x1, we have a total of n choices. So it's n choices for x1. We can choose any of y1 to yn. And then we have, for x2, how many choices do we have? We could still pick any one of these guys, right? We could take any of the yj's if you would. So there's still a total of n choices for x2. And for x3, we will also have n choices because we can choose any of these guys, and so on and so forth. Now, some of you might be wondering, wait a minute, I thought after we chose the first guy, there'll only be a total of n minus 1 for x2, because wait a minute, I thought if x1 chooses this guy, then x2 can only choose among the others. That is if we impose that the function is injective, and we're actually going to look at that in just a moment. But as far as functions themselves are concerned, we don't insist that the outputs, right, the outputs can have only one input. We do insist that the inputs have exactly one output. And for that reason, the number of functions from A to B is going to be equal to the number of choices of x1, scratch that, the number of choices for x1 times the number of choices for x2 times the number of choices for x3 all the way to xn, xm. I apologize for that, xm. So there are a total of m multiplications, so there are a total of n to the m functions. Now, we can write it this way. In fact, I'm going to just quickly write the notation this way because I've seen this notation appear before. There are a total of modulus of B, or cardinality of B options, for a total of how many times? Well, the number of inputs in A. So this would be the number of inputs in A. And what this means is that we're going to multiply the cardinality of B by A times, multiply that modulus of A times, cardinality of A times. And what that means is that we can actually, and I've seen this notation before, so basically we can consider the set of functions from A to B. We sometimes will denote this by B to the power of A, which is a bit strange because B and A are not numbers, they are sets here. But funnily enough, if you consider the number of items, you're going to get, by our previous calculation, whenever everything is finite, mod B, mod A. Right. Now, so there are a few ways to, there are few implications of this notation, but that's a bit more reserved for future courses. But this is a very common notation, and a lot of this notation arises from when we count. And I think it's a reasonable notation. Of course, it might be foreign if this is the first time we're seeing it, but it's fine, it's just notation. So these guys, I just want to emphasize, this is notation. Now, it's prior to talking about this doesn't really make sense, right? The notion of to the power of something only makes sense for counting numbers, real numbers, all that good stuff. So there's that. So that's the number of functions from A to B, and now we can ask a very similar question, which is not the number of functions from A to B, but the number of injections from A to B. So once again, now we're not just looking at functions, we're looking at the number of injections. And for the injective situation, this is where we need to be a little bit more precise. Firstly, if x1 were to point to any other number, now we don't have n choices for x2. Now we'll only have n minus 1 choices for x2. So this will become n minus 1. And instead of x3, instead of n choices for x3, it will be n minus 2 choices for x3. Repeating the process, you're only gonna get n minus m plus 1 choices for m, and we are still working with an assumption over here that n is bigger than or equals to m, right? N is bigger than or equals to m, and we'll have to, yes, and we'll need to come back to this in just a moment. We need to think about this in just a moment, because what happens if n is less than m? How do we make sense of that? So the number of injections from A to B, okay, in the situation when n is bigger than or equals to m, is given by n choices for x1 multiplied by n minus 1 choices for x2 multiplied by n minus 2 choices for x3 all the way to n minus m plus 1. So we can multiply all of that. And we can try to simplify this, right? And one way to simplify it will be using factorial notation. So we can check, and I'll let you guys check that this will actually give us n factorial divided by n minus m factorial. So I'll let you guys check that when we simplify the notation for factorials, we're gonna get this. In fact, let me just very quickly write out the I think I defined it later on, but it's okay. We'll define the factorial of a natural number by 1 if it's 0 factorial. Again, it's a definition. It's a reasonable definition. People make the case that that's the situation, but in some sense it is a definition. And you can define certain things, but for this symbol we give this meaning. And then for any other item, right? For any other item, for any other integer, you would take n multiplied by the factorial of the guy below it. So for example, and a very classic example here, 5 factorial is going to be 5 times 4 factorial, but 4 factorial is 4 times 3 factorial. 3 is 3 times 2 factorial, so on and so forth. You're going to get 5 times 4 times 3 times 2 times 1. So just a really quick mention over there about the factorial notation. So you can check that this equals to this in terms of factorial notations. It kind of works out very nicely. It's a good exercise to think about. Now, this is a situation when n is bigger than or equals to m. What about n less than m? That's a question that needs to be asked. Well, here's the thing. We've seen before that if there is an injection, okay, so let's just write down. We have a result before that we painstakingly proved before. If there exists an injection from A to B, then there has to be more items in B than A, right? So there has to be more items in B than A, which makes sense because if you're injecting into another set, in a sense, that set becomes bigger, in a sense, right? So there's that, but the size of B is bigger than or equals to the size of A. But in this situation, the size of B is n, and the size of the size of A is m. So in other words, if you can find injections, then n is bigger than or equals to m. Right, let me repeat that. If you can find injections, then n has to be bigger than or equals to m. So what if m is less than, well, n is less than m? This is precisely the negation of this statement. That means, this implies that if n is less than m, you cannot find any injections, right? there does not exist any injections. Right, that's just the contrapositive of the implication. This is the original implication, this is the contrapositive. And so, if you cannot find any injections, then how many injections will there be? None. There are no injections because you can't find any. So there we go. And that's the complete explanation for the result. So there's number of injections. It's a rather interesting expression, and we will find it useful in just a moment. Another question to ask is, well, if you want to talk about injections, naturally there are a few other types of functions, right? There's injections, surjections, and bijections. We're gonna jump ahead to bijections because there's something a little bit sneaky over here. We'll come back to surjections in just a moment. But for now, let's go to bijections. So we need to ask how many bijections are there from A to B. Now, the number of bijections from A to B, how many do we have? The first thing to observe is that bijections are injections and surjections. Right? So if we've already seen that there are a few situations that we need to concern ourselves with. If n is smaller than m, then we know there will be no injections. If there are no injections, you certainly can't have any bijections because bijections are injective. So you get none. On the other hand, if n is bigger than m, then you cannot get any surjections. In a sense, because this guy is bigger, right? So you can't really hit everyone no matter how hard you try. There's no way you can hit every single item in B. And if there are no surjections, and therefore there are no surjections, but if there are no surjections, then there will be no bijections as well. There's only one situation, and that's when n equals to m. And now, here's the question. How many bijections are there when n equals to m? Here's a result which we can sort of use. Right, so here's the claim. Let's just include a new claim here. We've calculated that the number of injections just now is n factorial over n minus m factorial when n is bigger than or equals to m. So, do we have a result that says that if n equals to m, then, well, in n equals to m, then the number of injections from A to B is n factorial over 0 factorial. In fact, it's m factorial, but you get the point. But you get 0 factorial, and 0 factorial by our notation refers to 1. Right, because over here, 0 factorial by definition is 1. And wouldn't it be nice if that is the answer? But we need to do, in order to do this, we need to check that the number of injections is the number of bijections. And it turns out that, well, here's the claim, that the number with the collection of injections from A to B is the collection of bijections from A to B under one condition. If A and B have the same cardinality and are finite. Once it's infinite, you don't get such nice results anymore. But when it's finite, you do get this result. And that is rather surprising. It's like, wait a minute, it works? Yes, it works. It actually works. And so, here's the claim. Now the question is, and I'm very interested in this question. Well, give me a moment. This is rather awkward and embarrassing. Okay, and the question here is that, can we prove it? Can we prove this result? Now, I'm going to, under this claim, if the claim is true. We get this result. And it turns out it is true. But we need to sort of establish this claim a bit more rigorously, a bit more properly. So let's try to establish this. Now we do have a few results from the stream on cardinality, right? We do have a result that tells us this. We know that suppose there exists a surjection from A to B that is not injective, then the size of A is strictly bigger, strictly larger than the size of B. And similarly, we have another result that says that suppose there exists an injection from A to B that is not a surjection, then size of A is less than size of B. But here's the really fascinating part over here, and that is this expression, right? So here's this aspect. By the contrapositive, if the size of A is bigger than or equal to the size of B, then any injection from A to B is surjective. Right? Any injection must be surjective. But that means if mod A equals to mod B, then you definitely will get this lower bound, which means that any injection must be surjective. And that tells us, let's just maybe prove this now a bit more properly. So here's a quick setup of our weapons of warfare, if you would. Now we will need to fix F inside the collection of injections from A to B. Since mod A equals to mod B, this tells us that mod A has to be bigger than or equals to mod B. But because mod A is bigger than or equals to mod B, this tells us that F is surjective. Which means that F is injective and surjective. And once you have F being injective and surjective at the same time, F must be bijective, which means that the collection of, that means F lies inside the collection of bijections. So we do get the one-sided subset from the collection of injections to the collection of bijections. Every injection must be a bijection because of what we have proved in cardinality. And I think it should be not too difficult for you guys to establish that this guy holds as well, which means that this equality is true, and we can count the number of bijections by the number of injections. And that's our answer. So it's a really, really sneaky result, and you can slowly verify that given enough time and energy and sanity. And it's a good way to revise some of your other topics as well. Logic, sets, all that good stuff. So we have the next question. We've already counted the number of injections. Now we want to count the number of surjections. And how do we go about doing that? Now the interesting thing is that the fact that they restricted B equals to 3 tells us that this might not be a really easy option. But here's the idea. So we're going to count the number of surjections from A to B. Now we'll just abbreviate by calling this 1, 2 all the way to M. And let's abbreviate this by 1, 2, and 3 without loss of generality. Well, the number of surjections, what does it mean for a function to be surjective? it means that everyone gets hit, right? Everyone here, every output has at least one input. That's what it means. Subjective. It might be a bit difficult to count it directly. So what if we took the total number of functions from A to B and we subtract out the non-surjections from A to B. Right? So that's the idea. What if instead of counting everything directly when it might be a little bit tricky to work with, we'll work with a simpler situation. We take the number of functions minus away the number of non-surjections. You might be wondering, wait a minute, how is the number of non-surjections any easier? Well, let's just look at the number of functions. We've seen just now, right? The idea of the number of functions is that every item here has exactly one output. There are a total of 3 possible outputs, so the number here is going to be mod b to the power of mod a. And in this situation, we're going to get 3 to the m. Let me just check to see my notation is correct earlier on. Yeah, okay, this is fine. Okay, so that's the first part. Pretty straightforward stuff. But now we need to count the number of non-surjections. So number of non-surjections from A to B. How many are there? That's the question, and it's not exactly an easy question to answer. Well, the number of non-surjections means it has to at least not hit some item. Correct? So it's the number of functions. So let's just think of it this way. Non-surjection means that there exists some integer in B such that f of any input does not equals to j. That's the idea of a non-surjection, right? It means you can find some output which has no input. So this raises the question, how many are there? How many are there? Let's maybe define something interesting, because this might be a bit interesting because there exists a j in B. So this is really fascinating, because what if, right, we were to define fj to be the, let's not call it fj, let's call it aj. Let's just call it capital Fj. Okay, so let capital Fj be the collection of functions from A to B with the special property that f of A is not equal to j for any A in A. That's the question, right? So if we define Fj to be all the functions such that you cannot hit j, then the number of non-surjections is the number of functions that either does not hit the number 1, or it does not hit the number 2, or it does not hit the number 3. Could be either one. Could be either one. And now we are trying to find the number of items in the triple union. That should sound alarm bell. The alarm bell should ring there, because this allows us to incorporate the inclusion-exclusion principle for 3 sets. Inclusion-exclusion principle for 3 sets. Once you have inclusion-exclusion principle for 3 sets, then we just need to count them up manually, one at a time. Now, how many functions are there that won't hit F1? That will not hit F1? Well, the number of functions that does not hit F1, the number of functions that does not hit 1 basically means that for each output, you can choose 2 other items. And you might be wondering, what if there are overlaps and whatnot? There's nothing to worry. There's a little trick up our sleeves. But for now, the first item has 2 choices. The second item has 2 choices. The third item has 2 choices. Each of the items here has 2 choices. And so, the number of functions is going to be 2 to the m. Because each of the m possible inputs has 2 possible outputs, either 2 or 3. Again, you might be wondering, what if there are overlaps? We'll come to that in a moment. I'll leave you guys to check that this actually equals to f2 and f3 as well. So you can think about why that's the situation. But now here's the slightly more interesting bit. And we want to sort of count f1 intersect f2. So let's maybe partition this guy like this. I don't know if we have enough space. Let me see if we can try to shrink things around. There we go. Shrink and shift it around. Now we're going to count the number of functions in f1 intersect f2. And what that means is that you want the functions that do not hit 1 and do not hit 2. This time you want to make sure it doesn't hit both. How many functions do we have? Well, for the first input, we have only 1 output. For the second input, we only have 1 output. For the third input, we only have 1 output. For the mth input, we only have 1 output. And so, there are a total of 1 to the power of m options, which is just 1. And once again, I'll let you check that this is the same as in f1 intersect f3 and f2 intersect f3. Alright, I'll let you guys check. Finally, the number of items in the last set. So essentially what we have done is we have split this counting into 3 bits, right? Into the first bit over here, into the second bit over here, and now we are on to the final bit. So for the final calculation, we want the functions that will not hit any of these guys. How many functions are there that will not hit any output? A function by definition means that there always must be at least 1 output, right? Every input must have at least 1 output. So how many options does 1 have? It has no options. In fact, there are no functions, right? There are actually no functions. So actually, there are no functions because every function, for every function, every input must have at least 1 output and at most 1 output. So if I can't even hit anyone in B, then there are no functions at all. So when we combine these items together, we're going to get 3 times 2 to the m plus minus 3 times 1. We're going to get 3 times 2 to the m minus 3 times 1. So that's the number of non-surjections from A to B. And finally, we can plug it all into our final answer because the total number of non-surjections is equal to the total number of functions subtracted by the total number of non-surjections. Right, this is the number of functions and this is the number of non-surjections. And I think you can generalize this approach for any number of surjections you wish. You can use the inclusion-exclusion principle. You can derive the general formula, which will take a bit of time, as you can possibly tell. It will take some time. Even then, it might not be so obvious. You might need to establish some formulae in order to use the inclusion-exclusion principle. I think it can be done because there's a bit of regularity that I can see some patterns in these numbers. Perhaps you can try it as an exercise, right? So let me know if you're gonna try it. Let me know in the comment section below. I think it's a pretty tedious exercise. It has no practical application apart from the fact that it's actually possible. You know, apart from the sense of achievement, it's not really possible. It's not really useful. So, or at least not useful so far from what I've seen. It may be useful in the future, but who knows? On that similar note, we can ask about the number of relations on a set, because we've been looking at relations and functions between two sets. What if it's just on a single set? So let's ask the question. Here's A, and how many relations are there on A? Right? And A, once again, is basically what we call an ordered pair. There are a few ways to visualize this situation, but I think what might help, because of the fact that we're doing counting, is to present the information in a table. So we will suppose, let's suppose that A is a collection of integers from 1 all the way to m. Again, this is just to make things a bit less notation cumbersome. You can always find a bijection, so you can do your thing, right? So we'll suppose this is the situation. And each box here represents a relation from A to A, right? From 1 to 1, and from 2 to 2, so on and so forth. I'm going to include 3 here because we probably might find it to be of relative use for us later on. Okay, so how many relations are there? Well, once again, the number of relations on A equals to the number of subsets of A cross A. In other words, how many subsets can we form from all these different options? For example, if I have all these different options, and I choose maybe a bunch of them, I don't know which ones, this gives me a relation. How many relations do we have? A relation, once again, is a subset of A cross A. So in other words, it is the number of items in the power set of A cross A. That simplifies to 2 to the A cross A. And the number of items in A cross A is going to be A multiplied by the number of items in A. In this situation, we have 2 to the m squared. Well, you could make it as general as possible and get the result. So that is the number of relations on A. And we probably would want to copy and paste some of this information because we want to at least keep this set up for future questions. Naturally, we have different types of relations. We have reflexive relations, symmetric relations, anti-symmetric relations. How many are there? That's the question. So, how many reflexive relations are there on A? Here we go. Suppose A is that. Now, number of reflexive relations on A. Reflexive relations on A means, well, let's recall what reflexive means, right? So what do we mean by reflexive? It means that for each item in A, you have the ordered pair inside the relation. What that means is that we must contain all of the diagonal items. This must always happen if we want a reflexivity. If we don't have at least one of these items, we are gone. We don't get reflexivity. The funny thing about it is that once we establish that we do need the diagonal items, you can freely choose anything else. I don't really care. The others are not really crucial to the notion of reflexivity. So the number of reflections is basically the number of subsets of A cross A excluding the diagonal. So let me just quickly define the diagonal here. Define D to be the diagonal formed by let D cross D, well, let D be this particular diagonal, right? So we basically want to find the number of subsets of the diagonal, of everything else but the diagonal, and that simply means that it's the number of subsets. So then ours is 2 number of subsets in 2 to the A cross A excluding D. And the number here is going to be 2 to the A cross A excluding D, which is 2 to the A cross A minus D. How many items do we have in A cross A? We've seen just now this is actually going to be A squared. And how many items do we have in D? It's actually 1, 2, 3 all the way to M, right? There's actually a bijection from D to A. So actually it's a total of A items. And once you have A items, then the total number is 2 to the M squared minus M. So it's almost like, it feels almost the same, except that you actually get something else. So that is the number of reflexive relations. We basically want to keep all of these diagonal elements over here. Alright, so that is the question. So let's copy and paste this again, and we're probably going to need this. And I probably want to keep the diagonal. The diagonal is a really useful construct here. So let's go down there. Now we want to find the number of symmetric relations, and this is where fun stuff begins. Okay? Now, what we can do here, and this is going to be a rather interesting experience. Okay, so firstly, we have A, and once again, we have the diagonal. This is the diagonal. How many symmetric relations are there on A? Now, symmetric relations, once again, we can visualize it as two-way streets, right? You can think of it as two-way streets and loops, right? You allow loops as well, right? Symmetric relations means every street is a two-way street, right? Every street is either a two-way street or a loop. So what does that mean? It means a bit like this, right? So 1, 2, 3, 4, and we have to go this way. We can loop to itself. We're allowed to do that. We're allowed to do this as well, right? Every street here is two-way, therefore it's symmetric. Now, how do we sort of convey this idea? So number of symmetric relations is going to be basically dependent on the mirror image, right? Essentially, that's the idea. So, how do we express this? Well, if we want symmetry, then we have, whenever we choose an item here, we automatically, well, we have a few options. Firstly, we can choose among the diagonals. We don't have to include the diagonal. For example, in this situation, the 3, 3 is included, but 1, 2, and 4 are not included. So in some sense, it looks a bit like this. That's fine. As long as we either choose among the diagonals or we choose pairs of diagonals. So if it's on the diagonal, we can choose them or not choose them. If it's off the diagonal, we must make our choices in pairs. Either we choose the both of them to be in the relation or not. Because we need to go from 2 to 1, and then we need to go from 1 to 2. If you just choose, say, this item here, then you are basically giving this situation, but this is not symmetric. So it's almost like the number of symmetric relations is equals, well, how do we think about it? Okay, it is the number of subsets. Well, let me think about this. Okay, so we'll do this way. The number of choices of diagonal elements, right? Diagonal elements times the number of choices of elements in the lower triangle. What do I mean by lower triangle? I mean this bit over here. The idea is this: if I choose one item here, then the corresponding vertex over here, or rather the corresponding point over here, I have no choice. I have to include the partner. And likewise over here, I have to include this other partner. This guy must include this partner, so on and so forth. All the choices really happen inside the diagonal, or in the lower triangle. Of course, the diagonal itself gives you choices as well. So, how many choices do we have on the diagonal elements? Well, we can either include or exclude the diagonal elements. So in other words, we have a total number of subsets, right? We can choose any subset of the diagonal element, and we can choose any subset of the lower triangle. In fact, that should be the point, right? So choices of is more like the subsets of the diagonal elements times the number of subsets of the elements in the lower triangle. And so what it gives us is that you get 2 to the power of mod of the cardinality of D times 2 to the cardinality of the lower triangle, if you would. Okay, so that's the idea. Now, how many items are there in the diagonal? We've seen just now, right, that the number of items in the diagonal is actually m. So we get 2 to the m. And how many items do we have in the lower triangle? Well, let's take a look. The number of items in the lower triangle is going to be 1 plus 2 plus 3 all the way to m minus 1. I think we've seen this before. This is actually the famous triangular numbers, and we can derive that via m minus 1 over 2, the number of terms divided by 2, times the first term plus the last term. This is what we call an arithmetic progression. There's a very clever proof by Gauss. In fact, later we're going to look at the proof of this result, so you can stay tuned for that. We can use literally whatever we developed to derive this result. This will simplify to m minus 1 over 2, m minus 1 over 2. So in fact, this is the answer, 2 to the m times m minus 1 over 2. I believe you can algebra your way through. This will be algebra to get 2 to the m plus 1 over 2. Now I think that actually makes sense because it's actually this triangle plus the diagonals. So it kind of makes sense, but it's fine. I don't think that's a big deal over there. So there's a number of symmetric relations. Again, this little table here is actually it's coming in really handy, I have to say. It's definitely a lot more handy than I imagined it to be. Alright. Once again, we can ask a question. How many anti-symmetric relations are there? Haha. And fun fact, I believe the number is going to be the same, if I'm right. And the idea is this. Right, so once again, we have the diagonals along this line with the diagonal elements and with the lower triangle. So the number of anti-symmetric relations. How do we know if a relation is anti-symmetric or not, symmetric or not? Well, it can include loops. It doesn't have to. We don't really care about loops. But if you have an item over here, you cannot include the other item. You have no choice. You cannot include the item. In the previous situation, when it's symmetric, you must include the other item. Now we're in a situation where you must not include this item. And that tells us that if we choose this point, if we include this point, we cannot include this point. If we exclude this point, we must include the other point. No, actually, we don't need to include the other point. Now I think about it. Okay, pardon me. Now, so let me phrase that again. Now, if you choose an item here, you cannot get an item over here. Right? You cannot get an item over here. You cannot get an item over here. But if you don't choose an item over here, you have free choice. You have a free choice of items which you want to pick on the other side. So, we're going to, this is a little bit complicated, but we are gonna consider this option here. Okay, so firstly, we're gonna count the number of subsets of this expression being chosen, okay, number of subsets, number of non-empty subsets. Give me a moment there. So let me try that again. Non-empty. Number of subsets of the triangle. Yeah, non-empty. Okay, this might be a bit confusing. So let's just try to do it again. Now, what we realize over here is that we have a bunch of situations, right? Okay, so let's just draw a picture over here. The first situation is, if we choose this guy, then we get this guy automatically. If we don't choose this guy, we can either... Okay, so there's one possibility. The second possibility is that we can choose this item here and then do not include it on the other side. Oh, sorry, give me a moment. Oh, yeah, there we go. The third possibility is that you don't include the guy in the bottom left, you include it on the top right. And the last one is that you don't include either option. Right? So these are the possibilities which you can make. Anti-symmetry basically allows for the remaining three situations. It does not allow for this situation of both happening at the same time. So what that actually tells me is that the number of anti-symmetric relations is equal to the total number of relations subtracted away by the number of relations that require symmetry, require the symmetric property. Right? So that's the idea, right? The idea is almost like, okay, if you have relations, or rather, you do not want to have relations with the symmetric property. Well, more precisely, strictly speaking, this still has a symmetric property, so we cannot just include that. We'll consider a number of relations that subtract away relations that come in pairs, right? The number of relations that come in pairs. Like, for example, I do not want to include relations that have these kind of elements. That has at least one pair, in fact. That has at least one pair. At least one pair. The moment I have a relation that has at least one pair, it's out of the window for me. Right? It's totally out of the window for me. And so, this might not be very easy to calculate either. Right? So, perhaps let's just try a slightly different approach. Now, let's first start with the number of choices on the diagonal, right? Subsets of the diagonal. You can choose the subsets of the diagonal. And now we need to ask for each point, what are the options that we have? Right? What are the options that we have? Right? So now, let's look carefully here. Let's call this point ij. In this case, we'll have I being bigger than j. And we need to ask, what are the options that we have for ij? We can either select it or not select it. If we don't select ij, we'll get two options for including ji or not. You can either include ji or not include ji. So let's just do it this way. Select ji or don't select ji. Right? You can do these three things. And once you select ij, you must not select ji. So that's the idea. What this tells us is that for any point over here, we will get a total of 3 different possible relations. The first possible relation is that we select ij and do not select ji. The second relation is that we don't select ij and we select ji. And the third possible relation is that we don't select ij and we don't select ji. So what this tells us is that we're going to get, for each item, we're going to get 3 to the power of the number of items here. It's not just a yes or no option, right? There's actually a third option, right? Which is within the no, you have 2 more options. So what this tells us is that we can either include or exclude items in D. So it's 2 to the size of D. And we have 3 possibilities for the items inside the triangle. This is a really sneaky result. We can apply the similar calculations from before. The number of items in the triangle is going to be m over 2, m minus 1. And there's not much algebra that we can do from here, but that will give us basically the final answer of the number of anti-symmetric relations. Alright, so now we want to look at what we call counting arguments, because we can sort of derive several interesting equations using counting as a proof technique. You might be surprised that, yeah, counting can be used to help us prove things. There are technical ways to do it, but we can prove certain equations using counting. So first thing to note is that we can choose the number of subsets. As you know, the number of subsets of size r is going to be n choose r. So for example, if you have a size 1, 2, 3, 4, and you have a possible subset 1, 2, how many subsets are there? So number of subsets of 1, 2, 3, 4 with size 2 is precisely 4 choose 2. And there will be some numbers which you can use. We've seen the definition of factorial, and now we can go ahead to proceed with what we call counting arguments. So now here's our claim. Well, I don't know why I did that. We have 2 claims, and we're gonna prove them one at a time. So let me just add more space there. Okay, well, I'm gonna do this later. We have this claim by Pascal. It's called Pascal's triangle, and it says this: for any r and n in the natural numbers, this expression holds. So sort of what's the picture over here that we have here? Here's the idea. If you draw Pascal's triangle, this item, which is corresponding, this item, which is corresponding to this number, will be the sum of the previous 2 numbers, right? So that's the heuristic, and will tell you which row it is. I think this will be the 0th row, 1st row, 2nd row, 3rd row, and then this is the 0th column, if you would. So 0th diagonal, 1st diagonal, 2nd and 3rd, and so on and so forth. So in other words, we are saying that at the n plus 1 row, right, this row n plus 1 and diagonal r is given by the sum of the 2 items in the previous row. Okay, so that's the rough idea over there. It's a rather interesting result, I have to say. And here's a very clever proof. I didn't come up with this proof, I learned this proof. And anyone who tells you that they came up with it is most likely lying to you. They probably learned it somewhere else as well. So here's the proof of this result. We'll let A be the set 1, 2, all the way to n minus 1 and n. Okay, so here's A. And we have two situations, right? So on the left hand side, on the one hand, what's n plus 1 choose R? Well, that is going to be the number of subsets, oh, n plus 1, oops. Let's just put an n plus 1 there. Subsets of A, because A has n plus 1 items, with size R. Number of subsets of A with size R. Now I like to think of it this way. I like to draw what we call a demand and supply table. So the idea is almost that for this particular number of subsets of A with size R, right, we have a total of, well, how many subsets do we have of A? Well, so let's just say all subsets with size R, right? Well, how many items can we choose from? We have a total of n plus 1 items. So that's essentially what we call the supply. And then how many items do we want to include in the subset? The subsets all have size R. So they have all R items. So the demand is going to be R. And, okay, how do we continue from here? Now, here's the really clever insight. We can split this up into two cases. The first case is that includes that these subsets will include the item n plus 1. Either a set includes n plus 1 or does not. Either includes n plus 1 or it does not. And if it does include n plus 1, then your subset is going to look a little bit like this. So S is going to have a total of R vacancies. If it includes n plus 1, then we are left with R minus 1 vacancies. We have one less vacancy for whatever other choices we have. So in other words, if it includes n plus 1, the demand, in other words, how many available spaces that we have, shrinks to R minus 1. We don't have so many spaces. One has been taken up by n plus 1 already. And since n plus 1 is in the set, we need to choose out of the remaining n items, so the new supply is going to be n. Right, new supply is going to be n. Now on the other hand, if it does not include n plus 1, then then we still have R spaces, so the demand on our side is still R. And now the supply, well, we don't want to include n plus 1. We don't want to include n plus 1. How many choices do we have to fill up our spaces? That's just n, right? It's still n spaces, n choices for the remaining R spaces. And so if there's n choices for the remaining R spaces, then we get the total number is going to be how many subsets of A that include n plus 1 is given by this pair of supply and demand. That's going to be this here. This quantity is going to be n choose R minus 1. And what about the other quantity? This is the subsets of A size R that does not include n plus 1. It's going to be these guys, and it's going to correspond to supply n, demand R. And would you look at that? These are basically the what we were trying to prove. So there are a few ways to prove this. You can prove this by induction if you would. That requires algebra. So you can just practice some algebra there. Or you could try this, what we call a counting argument, where you sort of break down this problem into two or more subcategories. You add them up. So I wouldn't say that there is a fixed proof technique, but there are some hints into how we can think about using counting arguments. The first one is the fact that, okay, we have a expression of the form something choose something. This tells us that we need to count subsets of some form. Secondly, we have a plus sign. And we need to plus two things. And these two things are going to be subsets of n with size r and subsets of n with size r minus 1. So somehow we need to sort of piece together all the pieces together to obtain our result. And this is how we do it. Again, I did not learn this proof. I did not come up with this proof on my own. I learned it somewhere, and now I'm just trying to apply these ideas into further proving. We've got one more counting argument up our sleeves, and then we can prove a very, very interesting result afterward. So here's our next expression. This time we're going to prove this one. We're going to prove this counting argument. Now, this looks really compact, so let's maybe first expand this out. What do we get here? We are getting 0 choose n plus 1 choose n plus 2 choose n. Well, sorry. 0 choose r, 1 choose r, 2 choose r, all the way to n choose r equals to n plus 1 choose r plus 1. Right, so let's just break it down that way so we can actually see things a little bit more clearly. And now we need to ask, how do we start? Well, the first thing to observe is that on the right side, what's n plus 1? Choose r plus 1. This is going to be the number of subsets of 1, 2, all the way to n plus 1 with size r plus 1. So maybe we can write out this over here. We can put the s over here. And we want to count the number of subsets of s with size r plus 1. So that's the question. Now we need to come here and ask what can we try to decode. So maybe we can put a demand and supply table here. So the total number of subsets is going to be, the supply is n plus 1 this time around because we have a total of n plus 1 items. And the demand, we have r plus 1 spaces. So that will be r plus 1. Now, somehow we need to reduce the r plus 1 problem into an r problem, right? Because on the right side, we have subsets with size r plus 1. That's on the left. On the right, we have subsets of size r. So somehow we are going to need to get rid of one number, correct? And once again, I must give a very clear disclaimer that I did not come up with this proof. Someone else came up with it. But here's sort of the idea. Okay, here's the idea. Now, for every subset of S, it's one of these guys, right? It has to be, all the items has to be here, which means it must have a maximum number. Now, here's the thing. How do you know which maximum number it has? It could be any maximum number, right? So in other words, we could ask, how many subsets of S with size r plus 1 where the maximum is n plus 1? In other words, we're looking at the number of subsets, size r plus 1, where the maximum now is n plus 1. So you know that n plus 1 is there, furthermore, is the maximum. How many items can you choose from? How many spaces do you have? Well, you initially had r plus 1 spaces, now you're left with r spaces. So now the demand is r. Now the maximum here is n plus 1. And what's the supply you're choosing from? The supply you're choosing from is everything except the maximum number. And if you choose everything but the maximum number, you have a total of n choices. You might be able to see where we're going with this. So that's the first situation. The maximum number is the biggest number ever. But what if the maximum number is smaller? say n. Now you might be thinking, okay, the number of spaces is still r. The number of spaces is still r, and then the demand, the supply, what we can choose from is still n. It's still n. Except that we actually cannot choose n plus 1. Because n is the maximum, right? If we include n plus 1, that becomes the maximum. So we actually cannot include both n and n plus 1. And that's a little trick there, because now, initially we have a total of n plus 1 items, but we need to get rid of these 2 items. We are left with a total of n minus 1 items. So our new supply is n minus 1. Well, what about if the maximum is n minus 1? Then your demand, how many spaces you can fill, is still r, it's not a problem. But now your supply goes down by 1 more. Your supply goes down by 1 more. So that gives you n minus 2 as your supply. And you can see where we're going with this, because we can repeat all of this until the maximum is just 2 and the maximum is just 1. If the maximum is 2, you still have r vacancies, but now you can only choose items smaller than 2, which is, you have 1 option, that's just 1. And if the maximum is 1, you have no options, so that's just 0. But why do we draw it this way? So let's do that. Number of subsets of S, size R, maximum 0. Well, maximum 1, sorry. Because now we can add up all of these items. We can add up all of these things, because the number of subsets in the total is the union of all of these possibilities. Every subset has a maximum. The maximum could be any one of these large numbers, these finite numbers. So if the maximum is n plus 1, we have a total of n choose r subsets. If the total number is, if the maximum is n, then we can choose n minus 1 r subsets. If the maximum is n minus 1, then we can choose n minus 2 r subsets, so on and so forth. 1 choose r. Let's add some more space. Zero choose r. But this is precisely the same expression as this. These two are actually the same expression. So we have proven this result. So how do we prove this result? Let's just quickly recap the strategy to do that. The strategy here is to first express this as, well, the number of subsets. Now you want to break down the number of subsets. And it does take practice, it does take experience. And the key trick on how we're gonna break it down this time around is to break it down into the maximums. Which one it is the maximum of. And so when you break it down to the maximums, you're gonna get this expression. This expression is equal to n plus 1 r, choose r plus 1. So there is a bit of a, almost like an Olympiad level kind of thinking needed for these kind of problems. I find myself rather weak at problems of this nature, but that's just my personal weakness. Now we can prove a very interesting result using this statement over here, because this is true for any r and n in the natural numbers. And so what we have here is that in the case when r equals to 1 n n equals to capital N minus 1, we'll just put it that way. Well, you know, this is fine. Set r equals to 1, something interesting really happens. We're going to get 0 choose 1 plus 1 choose 1 plus 2 choose 1 all the way to n choose 1 equals to n plus 1 choose 1. Now, what is n choose 1? Well, it is the number of subsets of a set of size n with one element. We have a total of n choices for that. In fact, 0 choose 1 is going to be 0, 1 choose 1 is going to be 1, 2 choose 1 is going to be 1, because if you have a set of 2 elements, you can only have 2 choices of a subset with 1 element, all the way till n. And this over here, pardon me, this is not 1, this is actually 2. N plus 1 choose 2. And we have a formula to calculate n plus 1 choose 2. That is going to be the first term times the one less than that over 2. But what do we have here? 0 is going to cancel out because obviously 0 is just nothing. We're left with the fact that the natural numbers equals to this formula. We have the claim of the sum of the natural numbers. And that is pretty cool. Using combinatorial ideas, counting arguments, we can prove a result that seems rather straightforward. Relatively speaking, it's a very not straightforward result for many generations. But that's interesting. Okay, so that is it for counting. And we're gonna use a little bit of counting to talk about graphs next time around. And we can explore graphs because graphs are a pretty useful way to represent information, especially in the applied math areas. Computer science, analytics, all that good stuff. In my undergrad years, I've never really used graphs, surprisingly. But I think I've seen people use graphs as a visualization tool for many types of proofs. I believe set theory will incorporate graphs quite a bit. We can also talk about combinatorial graphs and infinite, graphs and weird things, which is beyond me. I got a good undergrad math experience, mainly in calculus and advanced calculus. We call this math analysis and probability. So that's sort of where my training lies in. There's a whole long story as to why I ended up in probability, but that's for another day. So that's it for today, and I'll see you guys in the next stream on graphing. Well, not graphing, graphs.